Welcome to this course on getting to know the Vellum workflow. Vellum is a unified solver that offers fast production workflows for cloth, wires, soft bodies, balloons, and grains. It works a little different than other Houdini tools you may be used to, so this course is intended to help you understand the fundamental design intentions and usage techniques for this very unique solver. The Vellum workflow offers easy setup and control. It's OpenCL GPU accelerated, and has some very powerful visualization options as well. In this course, we'll explore some of the key nodes and concepts for working with Vellum, including configuring Vellum objects, creating collisions, understanding constraints, and understanding the post-solve workflow. Now, as a note, throughout this series of Vellum courses, I will be using some assets that were created with Adobe Fuse and Mixamo. Both are included with an Adobe CC subscription. However, due to legal reasons, we are not allowed to distribute all of these assets that you'll see. However, when we do encounter them in this tutorial series, I will walk you through exactly how to acquire them for yourself. So let's dive right in and start by looking at the different workflows for creating Vellum simulations in Houdini. Okay, here we are inside of an example file that I've set up. We're going to be working through this and building this on our own in the first few videos of this course. So I just wanted to show you what the end goal is here. What we've got is a piece of vellum cloth. Okay, above that we have some vellum wires. These are actually created using the vellum hair shelf tool. We'll talk about that in a little more detail later. Above that we have some vellum grains. And then above that a soft body. And you can see if you hit play that they all play very nicely together. They all interact and behave correctly. So like I said, we're going to build this together in the first part of this course. But I do want to point out that this is one of the files available on Houdini Insight, our educators' learning management system, where you're watching this video. And I just wanted to say that all of these files are super noted. Right? There's notes that explain each and every step that we're going to do as we create this. And I say this because if you're in a situation where you don't have access to this particular video, then you can always have this HIP file at your ready, and you'll have basically the bare bones outline of everything that you need to know to be able to teach a course or to be able to review if you need to prepare for something for the next day or week for a lecture. Okay, so let's go ahead and get started. I'm going to start with just a very basic blank Houdini scene. So I have nothing here. This is just the default launch with the build desktop. Now there's a couple of things I like to do to the desktop when I am presenting that make it a little easier for everyone to see. So I'm going to hit D on the keyboard while hovering my mouse over the scene view here. And I'm going to make my background black or dark here. And I'm also going to turn off this origin guide here, this origin gnomon as it's called. Just turn that off. The one here I always like a little bit better. It's out of the way, and I don't confuse it with any part of geometry or constraints or visualization data inside of my viewport. So this one's the one that I always use. So another thing that I also like to do is, let's lay down just a geometry node here. This is just an empty geometry node. But what you'll notice is on the parameters view that a lot of your parameters you have to scroll down to see some things. So these actually, you don't have a way of seeing everything that's available inside your parameters view. Also, your networks will get a little bit difficult. You'll find yourself doing a lot of panning over here. So I typically like to do things in a more wide view, since we do have a 16:9 ratio to work with in our viewport, with our monitors. So in order to do that, I'm just going to hover over this middle bar here on the far right-hand side, and I'm just going to collapse down that particular network view. Come up here to this top right panel, we'll split this left and right. And instead of this being a parameters view, I'm going to make it a network view. Now I can actually see the majority of my parameters without having to scroll down, and I can get a lot better view of my network here inside of this more vertical rather than horizontal layout for the network view. Okay, so I've got my empty geometry container, and I'm just going to dive inside, and the first thing I want to do is bring in the widget that we're going to collide with. So I'm just going to lay down a file node and come over here and browse to the geo folder. And there's my widget. So I'll bring it in. So we're going to use that just as something to collide with. Okay. And I'm going to use one of the new game dev tools, which is Game Dev Axis Align. And this is a really handy tool just for positioning things inside of your scene. And what the default does is it takes the bounding box of the object and moves it up so that everything on the object is sitting above the 0 level. You can do all kinds of different things with the object, but this is what I wanted to achieve for this. So it's just a really handy way to do it. I know you can do it with expressions and all kinds of other things, but when you have one node that does it by default, that's usually the best way to go. Okay, so jump back out here in this geo, I'm going to call widget. And that's all I've got in my scene right now is my widget. Now, I know I'm going to need a ground plane because I'm going to be colliding things and I want to have a floor for them to fall on. So I'm just going to go ahead and come up here to the collisions tab that's on this far right-hand toolbar. And I'm just going to lay down a ground plane. So I've just got a regular old ground plane in my scene here. Now, in the example file that I showed you, the ground plane had a color, and that was just so that we could see it separately from the cloth, like visualize it a little bit easier. You don't have to do this step, but I'm going to go ahead and do it. So on this ground plane object that we just laid down, very simply, I'm just going to lay down a color node, and we'll give it something bluish. Doesn't really matter. As long as it's not the default gray, I want to be able to see my cloth and wires and grains and everything a little bit easier. So that's the only reason I'm doing it. Okay. So first things first, let's create a grid that we can use as a piece of cloth and get that falling and colliding with our widget. So I'm just going to create a grid. Okay, we'll dive inside and we'll make a couple of modifications to the grid. First off, let's get it floating above our widget. And I'm going to give it a little greater resolution. So the resolution of your grid does define the resolution of your Vellum simulation. So if you only have 10 divisions by 10 divisions, that might not give your cloth quite enough resolution. So I'm just going to crank this up to 50 by 50 and we'll start with that. Okay. So now that I've got my grid and it's created up here, let's jump over to the Vellum shelf. And I'm just going to click on Vellum Cloth. Okay, I want to make sure my grid is selected. I can either select it here in the network view or select it in the scene view, either way. But as long as I've got it selected, I'm going to go ahead and hit Vellum Cloth. And some things happen. And we're taken immediately into the AutoDOP network that was created whenever we laid down our ground plane. Now I'm just going to kind of straighten things out a little bit here so we stay organized. Okay, dive back inside our AutoDOP network. And I'm going to tap L on the keyboard, and that will lay out all of the objects. So right off the bat, we see here we have our ground plane connected to a static solver, and it's merged in with gravity, and there's our final output. This is all very, if you've been through any of the other courses on the LMS that deal with DOPS, then this is all very, very familiar to you. And in fact, even what happened with the Vellum solver should be very, very familiar. Right, we always have an object, some sort of object that we can attach data to, and here we have the Vellum object. This is very similar to where if we had a DOP object or a POP object or anything else. And then coming into the far right side, we have the merge, so any other shelf tools we use will have that to wire into. But really the only thing that's here is this grid Vellum, which is a Vellum source. So we have an object, we have a source for the thing, and that's plugged into a solver, and the solver, of course, defines the rules by which this object that's sourced will play. Okay? But if we look at the source, all the source really does here is point directly to the grid geometry that we had just created. But it also pulls in something called constraint SOP path, which means that it's pulling in grid1 con. So let's jump out of DOPS for just a second and go and look and see what happened to our source geometry. Okay, so we've got some things happening here. I'm going to go ahead and tap L again to sort of lay out any crossed wires. All right. So we have some nodes here we haven't seen before. This cloth constraint node. Okay. Now it says that it's cloth constraints, and really what it does is it creates a relationship between each of these points on our grid. So if we turn on our points, we can see that we have, of course, pretty decent resolution, so we made it 50 by 50. And if we come down to the cloth constraints, we can see that we have this sort of cross-stitch pattern that's happening, right? Well, what this cross-stitch pattern actually is, if we turn off guide geometry here, all it is it's showing the relationships between the connected points. So in other words, this point has a relationship, if we follow the line, to this point. And it also has a relationship to this point, and it also has one with this point, and so forth, okay? So these little white lines that you're seeing, you might think of them as springs or matchsticks that are connecting each of the individual points on our grid together. And each of those little springs or connections have certain amount of properties to them, whether they're more or less flexible, allowed to stretch further, whether they have a certain amount of drag or resistance to them, whether they're allowed to bend in any way, shape, or form, right? So not only the distance, linear distance, but also the rotational information between those individual points. And we'll see a lot more of this when we actually start animating. This will make a little more sense. But what you see on the cloth constraints node are 3 inputs and 3 outputs. Now this is very important. This 3 in, 3 out philosophy is something that's a little bit new to nodes inside of Houdini. So what we have here on the far left-hand side is the vellum geometry. This is just the grid. Turn off points here. So all this is the grid comes in on the left. That information is used inside here to actually set up these relationships. If we dive inside here, you can really scare yourself a little bit, but this is how all of those relationships are set up, okay? Don't worry about that for now, and I would not show that to your students, especially if you're just now getting into DOPS or into Vellum. You don't need to dive inside there. That's just to let you know that all this is a series of other nodes, okay? So geometry comes in, a bunch of stuff is processed using that information, and then out we have the exact same geometry, so that when we start adding more of these nodes in line, we don't have to keep plugging this into each one. It's just automatically provided for us with this output. Okay, the same thing is true with this middle output, this pink output. But what this is, these are just the constraints without the geometry. So this is just the little matchsticks in between, right? Or springs or connections, right? So that's what we have created by the Vellum constraints node. It's taken a piece of geometry in, and it has defined a relationship between each of the points on that geometry that came in. And then it is supplying us on the outside with the geometry separated from the constraints and the constraints separated from the geometry. Now, this very far right-hand output and input are for creating collisions. And we'll talk a little bit more about those as we progress through the course. So now that we've got this sort of set up here, let's rewind our timeline, zoom out a bit, and hit play. And we can see that absolutely nothing happens with the widget, right? The cloth falls, it does interact with the ground plane, but it doesn't interact with the widget. And that's because the widget has not yet been made a static object. So we'll come up to the collisions tab and make sure the widget is selected and then click on static object. If we look inside our auto.network, we now have a new object that is connected to our static solver, and it's called widget. So now if we rewind and hit play, we have the interaction that we expected. All right, so everything seems to be working correctly. Okay, so the next thing we want to do is we want to create some hairs or wires that are going to fall on top of this cloth and also be interacting with the widget, the ground plane, and the cloth as well. So I'm going to come back up to the object level, and I'm going to create a new geometry container. And we'll pull it over here and set it beside the grid, and we're just going to call this wires. I'm going to dive inside. Now over here in my viewport, I'm going to look through my top viewport, which you can get here by select view and going to top viewport or holding down spacebar and the number 2. That will also bring you into the top viewport. Okay, so let's dive inside of our wires node that we have here, our geometry container called wires, and let's lay down a draw curve. Okay, now by default, what this allows you to do is just draw a bunch of lines on a generated plane out in space, and by default that projection plane is set to XY, so we can't see that from the top view. So we'll go ahead and change that to ZX. Now you can see that grid, which means that if we look here, we're going to be drawing, but everything we draw will be on that particular plane, which is great. So let's scoot that up just a little bit. We'll put it above our grid, and again I'm going to look through the top view and just draw some stuff here. So let's draw some curves. Now keep in mind, they don't have to stick in the borders of that template. That template is just giving you an idea of the direction that the curves are going to be, how they're going to be oriented. So I just drew some little squiggly lines there, and if we look, sure enough, they're attached, or not attached to, but projected onto that little blue guide that we have. But really they're just curves. So I have my curves here now. I can go back up to my object level, and we see the blue plane is gone. That was just there as a visualization. And I've got my curve. So let's grab our wires, come back over to the Vellum tab, and this time instead of selecting Vellum Cloth, we want to select Vellum Hair. So again, make sure you have wires selected inside of your network view, and then come up and click on Vellum Hair. Okay, so we're immediately taken into the DOP network that we created, the auto DOP network. I'm going to tap L on the keyboard, and that's going to lay some things out. Okay, so then let's zoom out and kind of take a look at what we've got. Well, we know what's happening over here. These are our static objects, and we know what's happening here. This is our standard stuff. Now, over here, what's happened is we've added a new thing called Wires Vellum. Okay, before we had Grid Vellum, the Grid 1 Vellum, that's referring to the Grid 1 object. That was our cloth. Now we have Wires Vellum, and if we look at the two objects, they're identical in what they are. They're just Vellum source nodes that are pointing to the original geometry and the constraints that have been created over in SOPS. Same exact Vellum solver. So cloth and wires here, or hair, as it is called on the shelf tool, are actually being treated in the exact same way. They're exactly the same thing. They're just relationships between points. And it's all connected to the original Vellum object. So even though we're dealing with cloth here and wires here, same solver and same data object are in use. This is why we call this the unified solver, right? Because it's one solver that can handle all types of different objects and simulations. So we're back here in Houdini, picking up right where we left off. We have our wires that have been created here using the Vellum hair tool. And we also have some cloth that we have created using the Vellum cloth tool. And now it's time to go ahead and generate some grains. Okay, so I'm going to lay down a sphere. And I'm going to dive inside. We're going to move that sphere up just a little bit in space so it hovers just above where the wires are. So we'll put it right here. And that looks fine to me. I'll pull this over here with our other source objects, and I'm just going to rename this sphere underscore grains. I make sure that I have it selected in my viewport, or in my network view, in my network view. You could also select it in the viewport either way. But just make sure it's selected, and then come over here and we'll do Vellum grains. And of course, some things happen. We're immediately brought into the AutoDOP network again, as all of the Vellum shelf tools will do. As soon as you apply them, you'll be bounced visually into the AutoDOP network. And instead of hitting L, I'm just going to drag this over here manually. But again, you can see the same thing has happened. We now have our grains and our wires and our cloth all being fed into the exact same singular Vellum solver. So grains are calculated in the same way that the wires are calculated and in the same way that the cloth is calculated. It's just a matter of setting up different constraint relationships between the points of those elements. So I'm going to jump back here to the object level and zoom out just a little bit. And we're going to scoot this over here. Now, it's really important what we're about to explore. Now, if you just want to see how everything works here, I can rewind and hit play. And of course, it'll just be a little bit to calculate here, but it will show you that everything is operating in concert together. The grains are working with the wires, are working with the cloth. They're colliding against the objects that we have that are static objects, including our widget and our ground plane. Okay, and it's all being done through a singular solver. Now, the thing about that makes it a little bit interesting is that all of this information is being fed into the DOPS arena here, okay, from these source objects, which all have a set of geometry and constraints that have been created for them. So where does this data come from? Well, we look at it here and we can dive inside of our sphere and we can see that we have what's called grains constraints, okay? Vellum configure grain. So this is the node that's setting up all of the different constraint relationships between the dots or between the grains themselves. Shouldn't say dots, but the grains themselves that are created inside of the sphere object as a source. Here's where you can set like the resolution of that particular simulation as well. So we can say our grain size, if we look up here, zoom in a little bit, our grains are just of an average size and we get a certain resolution based off of the shape of our sphere. If we want to change that, I can dive inside here and I can change that grain size to be much larger, like let's say 0.25. And now when I come back out to look, you see I have much larger individual grains, so a little less resolution defining the shape of the sphere and defining the intensity of the simulation, or the resolution, rather, of the simulation. Now what's interesting is that we had to jump back outside to see the results of that change that we made inside of this particular geometry node. And the reason for that is because we're working with a singular DOPS object. All right. And what I mean by that is the grid, which is our cloth. I'm just going to rename this grid cloth so it'll make more sense. Okay. So we have our grid cloth, our wires, and our sphere that makes our grains. All three of these objects are actually coming out of this one piece of data in DOPS, which is this Vellum object. Okay. So it's just one DOPS object that has three different sources, and each source has its own type of constraints that are set up to be unique to the way that it needs to behave. All right. Now, because of that, when we bring that information back over into the world of geometry for rendering, we do it with a singular import. So we're importing the geometry here. And what this means is that we're actually pulling it from the AutoDOP network, and the geometry that we're pulling is coming from the Vellum object 1. Okay? So it's not coming from just the cloth. We're not pulling from just the wires. We're not pulling from just the grains. We're pulling everything that's running through the Vellum solver into SOPS to be rendered in one singular node. So this says cloth Vellum on it. So it's a little bit confusing in the way that the shelf tools work, because when we turned this grid into cloth, it created this node, and it pulled in what it needed for that one piece of cloth originally. But as we've been adding to it with these wires and these grains, nothing has changed here. It's still pulling any information related to Vellum Object 1 into SOPS. Now, what is Vellum Object 1? Well, we can click the little shortcut arrow and it'll pull us over and show us right here. So it's anything associated with this piece of data. And we can see that everything associated with that piece of data is a solver and three different sources of things to feed that solver. Again, the cloth, the wires, and the grains. So the reason I bring this up is because it becomes interesting how you work with these things in a post-solve environment. And what I mean by post-solve environment is after the simulation has been done, you might want to add a smooth onto certain parts of geometry. You might want to run a detangle operation on certain types of geometry. Okay, post-simulation. So after the simulation work has been done, you can cache that information out to disk, right, which is done right here with this Vellum IO. This Vellum IO allows you to cache your simulation off to disk so that you no longer need to simulate, and you can work with saved data, okay? However, after you've done that, you might want to do some things to it here in this Vellum post process, which is already automatically created for you. Again, like we talked about, we might want to smooth it out with some subdivisions, or do some detangling to the collisions to correct that, or thicken the actual objects themselves. Now, the problem is some of these operations work fine with certain types of Vellum results, and other types of Vellum results it doesn't work so fine with. So we have to have a way of managing those types of geometry and what gets the Vellum post process and what doesn't get the Vellum post process. However, before we continue with that, I want to go ahead and create just one last type of Vellum for us to play with here, which is going to be a Vellum soft body. Or let's make a balloon. Actually, here's something to address, actually. So this particular course that we're watching, we're going to talk about how these things work. It's mainly about the data flow, how you work with these bits of information, how you can create Vellum to begin with. However, there are videos that are going to follow up after this course that will go in depth into how to control and art direct grains, how to control and art direct balloons versus soft bodies versus wires, how to build and drape custom clothing using Vellum cloth. So this particular course is not necessarily an overview of everything you're going to need to know about Vellum. So we're not going to go into the details of the differences between all the different types right now. I really want to focus on the data flow and understanding how to work with and create these things. So that being said, let's go ahead and make a balloon. So I'm just going to create a torus. And we'll scoot it up over here. It's going to be one of our sources, and we'll call it torus balloon. And we'll dive inside. I'm going to scoot it up just a little bit. We'll set it right above our grains, and I'm going to make it just a little bit larger. Let's see here, uniform scale. Okay, fantastic. And with the balloon selected, I'm going to come up here and click on Vellum Balloon. Now again, a very similar thing happens to what we've seen the last 3 times we've done this. We have a new source object, which has been created here called the Torus Balloon Vellum, right? And again, it's fed directly into the Vellum solver and the data is attached to the original Vellum object. And yes, we're going to do it one more time. Inside of the balloon object, we have a custom constraint that's been made for our torus. We actually have 2. We have one that controls pressure, so being able to maintain the interior volume of the torus, and another one that controls the actual stretch and bend of the constraints. Again, don't worry too much about all of these controls here. We're going to cover those in a later class in a lot more detail. But the key point here is that we start with our torus, we add our constraints, and then we have our original geometry, which is the torus, and then we have our constraints that have been created. Okay, same way that it's been done with the grains, the wires, and the cloth as well. All of that, of course, is fed directly into DOPS, and then out of DOPS, we bring it into SOPS using this import geometry to bring in the Vellum DOPS or Vellum object 1 here, and the constraints over here. Okay, so we're bringing in the constraints from the Vellum object 1 as well. And here you can see that we're bringing in the constraint geometry. All right, now these 2 pieces of information here are really for visualization. In fact, this is actually just a geometry visualization node, and it helps things look a little bit better in the viewport. We won't go into too much detail on these. We can talk about this a little bit later if it becomes important to you, but really right now you just need to know what these do is they make the geometry look a little better here in the viewport, and it affects how that works. The key thing though is this Vellum IO node. So the Vellum IO has 3 inputs. The first thing it looks for is the original source geometry, which we bring in from DOPS right here from the Vellum object. Okay. And then the other thing it looks for are the constraints, which again is the pink colored input. We pull that in from the constraint geometry from the Vellum object 1. And this third input right now is for collisions. Now we're not going to cover that right now. We are going to cover that by the end of this course, just not in this particular short video. But this is what allows you to cache this off to disk. If I wanted to right now, I could set a location. So let's go ahead and do that. We'll just say here inside of my testing area, my testing environment, I'm going to create a folder called Geo. And inside of that folder called Geo, which is already in existence, it's where my widget is, I'm going to make a new folder and we'll call it cache. Okay. And we will save out, let's use the same pattern as what we have here. So I'll just say cancel, we'll grab this piece of this and just add cache to include that new directory that I created. So I've got a separate place to save all of this off. And I believe that the majority of our animation is done by about frame 100. So I will let this calculate through here and save this off to disk and be right back as soon as the video is done. So I'm going to rewind back to the very first frame and change my end frame here. We're going to delete the channels and we'll just make it frame 100. And we're good to go. So I'm just going to click Save to Disk and I'll be back in just a moment. Okay, here we're back now. We have cached out our simulation to disk. I'm going to click on Load from Disk now, and what that's going to allow us to do is actually not have to simulate anymore. I can even turn off the brain if I want down here in the bottom to disable simulation. And I can take a look at my simulation. Of course, I can scrub through it now. It plays a lot faster since it's cached out to disk. I can go forwards and backwards. And I've got everything playing in conjunction and working quite well. Now, the thing you might notice about this simulation is that as we come through here and look at the actual quality of our cloth, so I'm going to zoom in just a little bit here, you'll see that we've got some jagged, sharp edges that don't look quite like cloth, right? These points have been simulated correctly based off of their constraint relationships, but they don't really tell the eye actually that this is a nice smooth cloth. Same thing is happening with the balloon. Very few balloons have sharp edges like these do around the edge. However, you don't want to have to feed all of that geometry into your simulation in order to get the behavior to look correctly. Really what you want to do is take this geometry after it's been simulated, which is the most costly part of the process, and you want to be able to do some things to it to make it look a little better. That's where the Vellum post process comes into play. Now, the Vellum post process allows you to do some things like smoothing and detangling, as well as allowing you to extrude certain pieces of materials like cloth by their width so that they actually look and render like real thick cloth as opposed to just singular planes of geometry. Now, there's a little bit of a problem with some of these, though. They work with certain types of Vellum objects well and not so well with others. For example, if I have the Vellum post process on, and I decide to turn on the subdivisions, let's do a Catmull-Clark subdivision, and we'll do it by 2, a level of 2. And as I hit play, I've still got pretty quick playback because I'm not simulating. I am actually drawing more geometry. And you can see that, wow, that cloth looks so much better now, right? We don't have those sharp edges anymore, but we're still able to maintain the original simulation data. Now, because it's cached to disk, you'll notice there's some kind of odd things happening with the way that the balloon works, because the balloon is actually bouncing off of some grains that are under here. But look at the geometry itself, so much smoother. It doesn't look hard and sharp to the eye. So, certain types of Vellum objects have reacted quite well to the smoothing process. However, we have absolutely 100% lost our elements that cannot handle smoothing correctly, like the grains and the wires. And part of the reason for this is because if you think about it, the grains themselves are just points in space. They have a relationship to the other points in space that they are a part of, like so the sphere that was the source for the grains. But there's really no way to smooth out or subdivide a single point. So trying to subdivide a single point doesn't really work very well. And it works, it's very similar to how the wire element or the hair, Vellum hair, is working as well. So as soon as you turn on this post process, it just absolutely destroys and eliminates them from the viewport. There are some other things as well that we can address, some other objects that get sort of befuddled by these things. For example, extrude thickness. You can actually look now at our cloth, and our cloth will have actual thickness to it. Here, you can see that. If we turn this off, there's not. However, that, even though it's being applied to the actual hair or wire itself, there's no extrusion happening here, right? There's not like there's a circle that's on the end that's being lofted along this line to give it some sort of depth. So this extrude by thickness operation, even though it's trying to operate on all the data that's coming in, has absolutely no effect on the grains or the wires. So how do we actually manage the data out of these 3 inputs and outputs so that we get effective post-processing happening when we're working with this unified solver? So we're picking up right where we left off with some post-processing problems, if you will. Pardon the alliteration there. What we need to do is figure out a way to manage the information being pulled out of DOPS so that before it goes into the post-process, we've actually extrapolated the things that can handle the post-process and those that can't. And really, this is just a matter of regular old SOPS geometry manipulation. Okay, so I'm going to lay down a couple of nulls to better explain what's happening, and I think that will make it a little bit more clear. So here's my first null, and we're going to call this one geometry. And we're going to make another null, and we're going to call it constraints. And we're going to have another null that we're actually going to use to represent this far right-hand side called collisions. So basically what we've got is this output here, which is the geometry. So let's slide this null in here so we know we're working with the geometry when we're working with this chain of data, okay? Now this middle one here is our constraints. So let's put this null in here so we can signify our constraints. And our collisions is the far left output. Now this is not something you necessarily need to do while you're working. Like if you're in a studio environment or if you're working on a project, this isn't necessarily required by any means. We're not changing data here or doing anything, but as a teaching example, when you're trying to explain what's happening to a group of students, or even if you're a student or you're learning for yourself for the first time, this is a really easy way to understand what's happening with your network as you're working through it. So I highly recommend doing this at least the first time that you demo this content to students that are seeing it for the first time. So what we want to do now is basically just remove and edit what's going into the Vellum post process, right? So I'm going to create a series of blast nodes, or actually just do it from within the viewport, to remove certain things that I need and don't need from going into the Vellum post process. So let's start with the geometry. So starting with just the geometry side, what I'm going to do is I'm going to pull out the surfaces that I can work with here that work well with my post process. So I'm going to grab the soft body or the balloon that we created and the cloth, and I'm just going to hit delete on the keyboard, which creates a blast node for me. And what I'm going to do is I'm going to say that this is going to be delete non-selected, which means it's going to remove the things I did not have selected. So what that does is it maintains the existence of the things that are going to go well into the Vellum post process. Now I'm also going to want to keep those other elements like the wires and the grains so that I can render them at a later time. Well, since I've already got a blast node that's removing those things, I can always turn off delete non-selected and I get just the objects that I don't want to pass through, correct? So let's just duplicate this. We can rename this as keep post parts. So these are the parts that are going to go through our Vellum post process. Now I'm going to hold down Alt on the keyboard and then just click and drag on this to get a duplicate of it. Okay, and this will say keep non-post parts. So over here we're going to uncheck delete non-selected. So now I have these things separated out into two different groups. I have a group that can go through post process, and I have a group that does not go through post process. All right. So that works out really well for us, actually. The thing is, though, we also have to handle that type of manipulation with all three of these outputs coming out of the Vellum I/O. Now, technically, we don't have any collisions in this particular scenario. So really, this collisions side of the output, we don't have anything coming into it right now, so we don't really need to worry about that. The collisions in this particular case are being handled inside of DOPS because we have static objects that we created with a static solver with the ground plane and the widget. Now we'll look in future videos as to how to use this input for collisions, but for right now we don't really need to worry too much about it. So this collisions is kind of out of our sight for right now. I'm glad that we marked it because we now know exactly what these inputs and outputs are, but with no data coming in, we're not concerned about this particular bit. The thing is that these constraints that are coming through include all of the constraints. You can see that here just by clicking on the null. All of the constraint data for the cloth, all of the constraint data for the grains, all the constraint data for the soft body or the balloon, and as well the hair. Well, we don't want to process all of those types of constraints. We don't need to feed all that data into the post process. We want to work as efficiently as possible. So again, we only want to keep the constraint data for the things that we need. So we want to remove the wire and the grain elements, which we can actually select right here. And you'll notice that it's just actual geometry. So I can actually come in here and grab those things. All right, we'll grab, this is going to be our Vellum hairs, which we don't need to feed into the post process, so we can get rid of that. And we also want to grab our points here and get all of our grains, and we can delete those. So we've got those things now have been removed from any part of the constraints. Okay, so now our constraints can be fed into the Vellum post process and work absolutely efficiently. Now, this part of the process is not necessarily required to remove these constraints, but I just think it's nice to work cleanly and to remove any data that you don't need from the chain so that everything can work effectively. Okay, so now that we have the Vellum post process being fed only the things that we want, we can actually turn on our subdivisions, and I'm going to leave these at a smoothing depth of 2. I don't really need to get into the detangle. I am going to extrude them by the thickness though, because this is going to allow me to get a little bit more depth here on my cloth, and I like the way that looks. So that's all good. And again, we will be covering these actual settings and what this does in a later video course when we get into the cloth draping and cloth simulation stuff. So now that I've got this data separated out in a way that makes sense, I need to merge back in the pieces that could not handle the Vellum post process. So I'll just create a merge, and we'll bring those in, and we'll bring in the stuff with the post process. And now I have a simulation. Let's turn off the grid just for better visualization over here. Now I have a simulation that is cached to disk, which happens here at the Vellum I/O. I've separated out all the types of data that are cached to disk. So keep in mind, this is another thing to keep in mind, especially if you're working on smaller machines like student laptops, or if you're working on something in the lab that might not have as big of or fast of a hard drive. When you cache out this Vellum IO, you're not just caching out the original geometry, but you're actually caching out the original geometry and the geometry that makes up the constraints inside of it as well. So these will be a little bit bigger caches than you might be used to. So just keep that in mind as you're working. But now that we have all of this separated out and made correct, we can come back here and hit play, and we get fairly fast results from all of our geometry already cached to disk. Now keep in mind, we've subdivided twice the geometry for the balloon and for the cloth, and we've extruded the cloth, and the cloth is actually not causing any major problems with tangling, not causing any major problems interpenetrating with other pieces of geometry. We have nice smooth surfaces, and we have 3 different types of simulations: wires, cloth, or 4 wires, cloths, grains, and soft bodies, all working together inside of one unified solver. Now that's pretty cool. That is definitely a neat way to work using the shelf tools and using DOPS the way that you're used to. So if we stop this here, we've seen the playback. I'll rewind and go back up to the object level. So again, we have all sorts of sources. We have a single piece of geometry that's brought back in that contains the results of the AutoDOP network for all of those things, right? So this is one way that you can work. However, it's very important to mention that the Vellum solver can be created right at the geometry level. Right inside of SOPS, I can lay down a Vellum solver. So there's no need to go into DOPS. This Vellum solver can handle all of the simulation techniques for any of the things that you create inside of SOPS, right? So it introduces a whole new way of working with cloth, wires, and grains and soft bodies. In other words, you could be running a version of Houdini that is not a full-fledged Houdini effects. You could be running Houdini core and still use the solver element because you can implement it right at SOPS level. So Vellum is something that can be done at a lower version of Houdini. So if you need to work for cloth for something, especially if your students are working for their demo reels and they want to do some cloth projects or grains or wires and fur and grooming and using Houdini, then they can actually use their core licenses, which are a lot more affordable, and do that because Vellum can be implemented right at the SOP level. So here we are in Houdini, and I'm going to start right at the object level, okay, and lay down a brand new geometry. So this is just a new geo container. We'll call this simple setup. You can call yours whatever you would like. I'm just giving something for some type of reference, okay? So I'm going to go ahead and create basically what is going to be a flagpole, and we're going to do it without using the shelf tools, and we're going to do it without going into an AutoDOP network or even looking at DOPS in any way. We're going to create an animated flagpole with waving cloth, and we're going to do it all right from within SOPS, laying down our own nodes as we go. It's not as complicated as you might think. I've seen people try to recreate DOPS from scratch, and it does get a little bit hairy sometimes, but we're going to make it super simple. It's all right here at SOPS level. So the first thing I'm going to do is I'm going to create a grid. This is going to be the actual cloth that I use for my flag. And let's zoom out a little bit and we'll get a look at it. And I'm going to make sure that it's oriented in the XY plane, okay, for my flag waving. And let's go ahead and make some general changes to its shape and size. So we'll say, yeah, that's good. And this will be, yep, there's my flag size. That makes a lot more sense. And let's see here. We'll give it some more rows and columns. We'll give it a 20 by 30 just so we've got some actual resolution to work with. And I can see that a lot better if I will turn on my smooth wire shaded there. So I can see I've got a little bit more resolution to feed into the Vellum solver to give my cloth a little bit better behavior. Okay. And I'm not sure where it's going to sit on my flagpole yet because I haven't created that. So let's go ahead and do that now. Let's create our flagpole just by laying down a tube. And I can template this by using this little pink flag or the second flag over here, and I'll be able to see it as I begin to work on the tube itself. So there's my flag. And now let's build the tube. So the tube itself, I'm going to make it polygons. And let's go ahead and give it end caps. That's good. And how tall do I want this to be? Well, I don't really know yet. Let's make it X high. Of course, it's way too big around, so I'm going to make that 0.05. And we'll just make it, yeah, sure. Let's say 5 units high. Now, I want this tube to be able to sit right on the ground level and not be halfway above it and halfway below it as it is right now. And there's a really handy tool that's a part of the game dev tool set that will do this for me. I know you can write bounding box functions. You can do all kinds of things, offset the height, the center by the height, and all kinds of different things. But there is one really cool tool that's part of the game dev tool set. Now, if you don't have the game dev tool set, I'll give you a really quick rundown on how to get a hold of it. If you come over here to shelves, I'm just clicking on this little plus button at the top of the shelves. Go to shelves and make sure that game dev toolset has a check mark by it. And when you do, then you can come down here and click on game dev toolset and you'll see this toolbar. Now, if your toolbar does not have all of these icons, all you have to do is click on this icon that looks like a joystick. And you'll get a little dialog box that'll say, hey, let's update some tools and make some tools. Click update. And as soon as you're done, it'll ask you to restart Houdini. So be sure and save any work that you've done, close out Houdini, and when you restart it, you'll have access to all of these new tools that have been created by the game development team. They're really handy, especially in cases like this, where it will save you and students so much work when you can actually just get to creating really cool content by using some of these tools. The one I'm going to use is an axis align. So game dev axis align. I can lay this down, connect it up, and just all of a sudden, without having to do any sort of expression writing, copying, pasting, dividing by 2, any of that stuff, this node will just automatically take the absolute minimum of the y-axis, which you can see here, and center it. Boop. It'll do all kinds of other things too. You can play around with these as much as you want, but when you've got a node that does everything for you by default that you want done, there's no reason not to use it. Okay, so I'm going to reverse this situation and put my template flag over here on the axis align and look at my grid, and let's get our flag up into place so that it's positioned a little bit better. So I'm just going to use my handle tool now. We'll move our grid up so that it's in a good spot by the flagpole. And that looks about good for me, just for what we're going to do here. Maybe scoot it up just a little bit. Okay. Awesome. Now, let me look for just a second here. I'm going to add some more resolution into my flagpole, just because we're going to be using it as a collision object. And if I look at it right now, the way that it sits, we'll untemplate this, there's not a lot of subdivisions in the y-axis at all. So I'm going to go ahead and just add some more subdivisions into my original source tube. Here, we'll give it 20 by 30 in rows and columns. So we now have a little bit more, separation here, a little more geometry that we can work with when we're working with our collisions and pinning things together, as we will when we work with this flag. Okay, so there's my flag, and here is my flagpole. Now, how do I get these things working together? The way that we've done it before is we would have come over here and, oh, looks like I renamed my tube by accident. There we go. So what we'd do is we'd grab this grid and then we'd come up to the vellum shelf and we would turn it into cloth here. But what that does is we know is creates an automatic dot network out here in the nothing that we have to play with. Then we have to come in here and re-import that geometry, separate out anything that we want or don't want. We have to set up the flagpole as a static collision. Then we'd have to figure out how to make constraints between those things inside of DOPS. And that's just a process that sometimes is necessary, but in this particular case, we can develop a lot quicker and do a lot more iterations just by building this up here in SOPS. So in order to do this, I need to tell this grid that you're vellum cloth, okay? So all I can do is just tap tab, vellum, and there's a vellum configure cloth node right here at SOPS level. I'll just lay that down, connect it up, and guess what? I've got cloth. I can already see the constraints that have been created between the points on my grid, right? So I know that those constraints have been created. I know that information is available to me here. If I was to lay down a null, I'd see the constraints. And I know that here is the output of my geometry from my vellum configure. So we've seen that in action before. Everything is good there. But if I just click play now, of course, nothing happens because we're not actually calculating any simulation data. All we've done is we've set up the geometry for the constraints for this to be a piece of cloth. So what we're going to do now is we're actually going to lay down a vellum solver, which is right here. Okay. Now, of course, you'll notice the vellum solver has 3 inputs and 3 outputs. Well, let's go ahead and connect those things together. So the geometry into the geometry, the constraints into the constraints, and the collisions into the collisions. We don't have them yet, but guess what we're going to do here in a second? We're going to add this flagpole as a collision. But for right now, let's just see the results of what happens when we hook up the Vellum solver. If we click play, well, the flag falls as we would expect it to. I think we're seeing, let me just double check this here. There we go. Okay. So yeah, the flag just falls as it was supposed to. I had a little bit of an OpenCL glitch there for a second where we saw the flag drawn twice in the viewport. That's probably my poor laptop that's struggling right now. So we've got this Vellum solver down now. Now let's take a look inside the Vellum solver. We probably want a ground plane for something to be able to collide with, right? But I don't want to have to come up to my collisions tab and create a ground plane because, as we know from previous experience, that's going to create an autodop network up at the object level that we now have to deal with all kinds of ins and outs with dops. So built right into this Vellum solver SOPS node is the ability to add a ground position. So we can click this on, and now we have this ground plane that's represented by this blue grid here at the bottom of our scene. So if I rewind and hit play, my cloth now hits the ground, and I have a ground plane that's effective for me to work with, again, without ever having to go into DOPS under any circumstances, okay? There are some other things that the Vellum solver will offer you as well. If you look here, there are some forces that you can play with. One of them is gravity. So the reason that this fell automatically was because we had gravity turned on inside of the Vellum solver. By default, it's just turned on. But we also have this wind that we can play with, okay? So I'm going to blow my flag around a little bit, and we'll just blow it around, let's say, in -5 of x. And we hit play, and it pushes a little bit. Let's give it a little bit more strength. We'll say -10 for our wind. And now you can see that we're falling at a diagonal, and even after it hits the ground, the wind is actually pushing the cloth around still. So the very last piece of this would be to add in the collision geometry of our flagpole. So here's our flagpole, and here, this input on Vellum cloth is asking for the collision geometry, okay? So let's go ahead and hook that up to our flagpole. So now when we come down here and hit play, oh, you'll see that the cloth itself is wrapping around the edge of the flagpole here, okay? So the flagpole has become a piece of collision geometry. So basically, the flagpole is a static object, right? So we have created a ground plane, a static collision object, and a Vellum object, all with 2 nodes inside of SOPS without ever having to go into the land of DOPS or having to worry about data exchange between the 2 worlds or any of that kind of stuff. And what we want to do is we want to make this flag actually look like it's attached to the flagpole. And right now it doesn't, it just falls. There's a couple of ways that we can do this, and they're worth exploring these 2 scenarios. So let's say in this first example, our flagpole isn't moving. It's in the ground, it's permanently in concrete in the ground, and we just need to attach the flag itself to some points in space, just pin them in space so that they stay stable, right? Well, we can do that inside of the Vellum cloth node just by coming over to this pin to animation where it asks for pin points. We can come over here and click this button and start grabbing some points in space. I'm just going to rotate around a little bit, and we'll grab the top few points here. Say the top 4 here and the bottom 4 here. Some shift and grab these points as well. Now when I hit enter, it will populate these pin points over here. Okay, so now I can zoom back out. Look at my flag setup. I'm going to change my selection point over to primitive so those points aren't visible anymore. And we'll click play. And what you'll see is that those points are now actually pinned in space, right? Now they're not exactly pinned to the flagpole. They're just pinned in 3-dimensional space. Okay, so it's sort of effective for doing things like this. If you had curtains that you wanted to pin to something, you could actually just pin them in space and they'd be stagnant, and that would probably be just fine. It would probably look just great. In fact, if we change our wind direction inside of our solver from -10 to 10 and click play, this actually doesn't look too bad. I mean, this looks like a pretty good flag, and we don't have to set up any other nodes. We're working very lightweight. We can now start to iterate quickly on how we want our wind to look, how much strength we want our wind to have. start playing around with the actual cloth itself as far as the stretch and bend, what kind of material is the cloth made out of, working with these constraints. And again, don't worry too much about this information right now. We're going to cover it all in a lot more detail as we get into these other courses in the Vellum series. But right now, I just want to show you that you can use this vellum cloth to pin certain points down to certain things. So that's great, but what happens if we actually have our tube that's moving around? So I'm just going to use a little transform node here. I'm going to put it in line with our tube, and we're just going to use a very simple sign of $F, I think probably something like times 10, and we'll just see what kind of motion that gives us. Let's look at our, that's pretty quick. Let's maybe slow that down just a little bit. Let's say instead of 10, we'll make it 6. Okay, that works. That's something we can do. So there's our flagpole with a little bit of motion on it. So what happens now when we look at our Vellum solver and hit play is nothing like what we want. Okay, so what's happened is that those points in space on the cloth are keeping it pinned right there at those coordinates, and the flagpole is just randomly crashing into the cloth, tearing it, doing all kinds of fun stuff to it, which we don't really want in this scenario. So how do we fix this? Well, the thing is we don't want to pin these points to anywhere in the middle of space. Okay, so I'm just going to clear this out. There's actually a node that's really, really handy for this, and it's called the Vellum attached to geometry. Okay, now I'm going to lay it down out here on the side to start with, and just take a notice this node real quick before we hook it in. It's got 3 inputs and 3 outputs. First input, geometry. Second input, constraints. And the third input, the collision geometry. So instead of having to wire these up manually, 1, 2, 3, and then 1, 2, 3, which you can do. I'm just going to hold down Y on the keyboard to get the little scissors and then drag across those to cut them. The new Vellum system is smart enough that if you drag this 3 in, 3 out node right over the 3 inputs and outputs, boop, they automatically will snap together and wire them all up for you. So you don't have to do that manually. So that takes a little bit of the headache out of it, right? Okay, so here's our Vellum attach, and it's great. We've got it working here. If we hit play, well, it's not quite exactly what we expected, but it's pretty close. Let's go ahead and wire this up so that we can see the results of both of our things. So I'm just going to do a little merge node here. And I'm going to take the results from the Vellum solver, which is going to be our geometry. And I'm going to grab the collision geometry, which is the flagpole. So now I can see both the flagpole outside of this Vellum workflow, which is coming in, and the Vellum cloth itself coming in over here, right? So when I click play in the viewport, I do get something that looks pretty good, like it's behaving pretty accurately. If I want to, I can even reverse the wind on the Vellum solver. Let's give it a little bit different direction. We'll give it a -3 here. We'll give it a 2 here, and we'll just see what happens when we click play. Okay, so we're getting a little bit more interesting look. What happens if we get rid of the wind altogether? So it's behaving a little bit interesting for us. Right, so there's points of this that are not falling or behaving the way that we want them to. And that's because as it sits right now, this Vellum attach cloth is trying to attach every single point that we have to this flagpole with some sort of rest length of distance to keep them apart. And by that, what I mean is that if we look here, before we do the Vellum attach, our cloth is actually sitting right inside or on our flagpole. So let's move our grid a little bit away. So I'm just going to grab this, and I'm just going to scoot it away from the pole a little bit, okay? I'm doing this so we can illustrate how these constraints are working. When I turn this on, immediately, and come down to the results here, our final results, and we click play, you'll see that that distance, that separation distance is maintained. Okay, so the cloth, the edge of the cloth did not automatically snap to the pole. It's actually maintaining that offset distance. Well, the thing is that those edge points are maintaining that offset distance, but so are the points all throughout the cloth. So this set of points is maintaining its offset distance. This set of points is maintaining its offset distance, which means that our flag is not necessarily falling correctly. It's trying to maintain its stiffness along the x-axis, okay? And that's something that we don't really want. That's a behavior that we do not want. What we want to be able to do is to define the exact points that we want in here and tell them to attach to the closest part of the pole and let the entire rest of the flag behave on its own with gravity and other forces that might be in the scene. So here on the Vellum attach node, we can tell it exactly which parts of the geometry we want to use to snap over to the pole itself, okay? So I'm just going to say points over here, and I'm going to use my little selector, and I'm going to go over here and grab, just as we did before, scoot in a little bit, you can see a little better. I'm just going to grab these top 4 points, and then again hold down Shift, and grab these bottom 4 points, okay? And they've turned yellow, showing me that they are selected. When I hit Enter, it populates this group, and I can automatically see that there's some new constraint geometry that's been created, right? I see these little wire connections that exist between these points only and with the first bit of geometry that's found onto the flagpole, okay? So that's automatically being worked out for us. It knows in which direction to try to find its constraints. It knows where to find its constraints, okay? Now, if you didn't want these 4 constraints to be attached to the closest point of the collision geometry, which is how this is done right now, you do have the ability to define where on the collision geometry that you want those points to seek out the most logical connection. So I could come into the tube. Let's do this before we transform it around. So here's my tube, and I'm going to look at the tube, and let's go ahead and select some primitives. And I'm just going to grab some in here. We'll say these. Oh, I need to hold Shift down when I do that. Gets me every time. So there, I've got some faces selected there. We'll come down here just randomly and we'll select some faces here. Okay, hold Shift, get that one in the middle. There we go. And I'm just going to create a group out of these selected faces. So I'm going to do Tab GROUP. And I've got a group, and we're going to call this Attach GRP. So now over here, let's go ahead and look at our final results. All right, here's my Vellum attach. As default, it's trying to connect to the closest point on the closest piece of geometry. But I can tell it here my target group that I want you to actually try to find. Why don't you use that attach group? So now you'll see what's happening is the flag is actually seeking out the closest part on either of the groups that we had selected to attach the flag geometry to. Okay? So you have complete control over what points of the cloth get connected to what points of the collision objects. Now, I don't necessarily like this setup connection. I just wanted to kind of show you how you can do that by selecting pieces of geometry. We'll look at an example here next where that's really effective and really cool. But for right now, I'm going to remove this attach group. We'll let it do its normal thing here. And now let's come back, look at our merge node, and click play. So now our flag is behaving more like what we would expect it to, right? It's falling correctly. The geometry is not trying to maintain its offset for each and every point on the cloth. We do have it following the animation. It is attached right at these points, which is perfect. The only thing that I would do here to adjust this would be, what if I wanted those points to not have that offset distance? If I want the flag directly attached to the pole at the points that I selected. Well, that's simple enough. There's just one thing that needs to be adjusted, and that is this rest length scale. Now, this rest length scale, all it's doing is it's saying for the constraints that we just created, right? This attachment constraint for attaching this to this, in other words, the cloth to the pole, that rest distance or the initial offset distance, okay, which is this. Right now, if you have that rest length scale to 1, it will maintain it forever. So we can set that to 0, and it will say, do not maintain that offset at all. In fact, on the first frame of animation, click, you'll notice that the flag is immediately drawn to the edges of the flagpole. Okay, so we don't have any rest distance whatsoever. And we can see that if we hit play now, these points in the middle here are still allowed to offset. right? So these points are offset from the pole, but these points here are drawn directly to the edge of the pole, right? Now you might see a tiny bit of gap right there. Some of that is the offset distance. The extrusion of the actual materials. If you run down a post process and extrude that by the thickness, you'll see that that gap will close right up. Again, we'll talk about more of those things as we get into further courses on Vellum, which will be out soon. But for right now, I just kind of wanted to show you this SOPS workflow. Again, we did this with 3 Vellum nodes. We were able to create a flag, add some forces, create a ground plane, make some attachments to the constraints, and immediately get working results with just 3 nodes. And I didn't really adjust anything in any of these nodes except for telling it what points I wanted to attach and how I wanted them to work, right? So here we are back in Houdini, and the file we're about to take a look at is called Cape. It is included in the assets for this course. So I just want to point out that what we're going to do here is we're going to add a cape onto a character that has some animation. So don't worry too much about the setup of the character. When we get into the cloth course, we're going to talk about how we start with a T-pose, how we merge in animation, how we blend that together so that we can go from T-pose to animation, how we set up individual collision groups, how we actually draw the cape itself. So we're going to pattern make with a cape, and I'll actually walk you through it very quickly in this lesson. I just want to show you the tools that we've been working with in SOPS, the Vellum Attach, the Vellum Cloth, the Vellum Solver, a little bit of post-processing, and then some materials right here. This is all that we do to make the animation of the cloth work with the character. So I'll play through this just very briefly, and you'll see that our character goes from a T-pose into a fighting stance, and then has sort of this fake fist fight with nobody, right? So T-pose, where we build the cloth, then into the animation where we actually see him fight. Now this is Tommy. You can get Tommy anytime you want just by hitting tab, T-O-M-M, and you can download the Tommy test geometry. He actually ships with Houdini, so the model itself we can actually ship with. That's not a problem at all. Now the animation itself comes from Mixamo, and I'll show you exactly how we got to what we have here. So you can upload your own character. So all I did was lay down a Tommy inside of Houdini, export him as an FBX, and then import him using Mixamo. And then here I can look for any number of animations. You know, there's all kinds of fun stuff that you can make your characters do here. There's 26 pages. I've got 96 to a page. So what is that? 2,700, some bunch of animations that you can download and play with. So I highly recommend you testing your cloth with different types of animations, all of your different character animation sequences or character effects sequences that you work on. You can work with Mixamo, which is great. So F-I-G-H-T, if I type in fist fight, you'll see that we got fist fight A here. So I just click on fist fight A, and now I've got Tommy doing fist fight A. And that's the animation that you're seeing in Houdini. So I just downloaded it here. It brings in an FBX. Let me close this out, and we'll reopen Houdini here. So it brings in an FBX, and I just merge in that FBX animation that I need, and I'm good to go over here. So really all that happened in the prep of this character, again, don't worry too much about the details. We're going to go over this when we get into the full cloth draping course. But all I did was make a group for the pants, a group for the shirt, give those a red and black color. And then I made a special group on my character. And we can see that if we look here. Okay, so this base group right here, these are the points in which I want the cloth to attach to, just like when we had those on the flagpole, and I decided that I wanted to have a certain point on the flagpole that the geometry would connect to. That's all that I did there, was select a particular group of primitives. Now, the cloth itself, we'll rewind this back to frame 1, this will make a lot more sense. There we go. So he's got a red shirt, he's got black pants, and I want to create a piece of cloth for him. So I draw a curve that is half of my pattern, all right? And my pattern being a cape. So I draw half of it, and then I resample the curve so that I get a better, smoother looking geometry out of it. And then I just do a quick little adjustment of how I want that curve to look. I mirror that so that I now have a piece of cloth that's shaped like a cape. I use a fuse node, and that seals these points together at the very center where I had the two pieces. Now I have one continuous curve. From that continuous curve, I can create a planar patch. That planar patch basically fills in all of that shape outlined by the curve with triangular geometry, which is great. There's a lot of options here that you have for resampling your curves and adjusting the edge length. Again, we will talk about that when we get into the character course, or I mean into the cloth itself course. Then all I do is I just take it back a little bit so that it sits off of the character behind him, okay? And that's my cape. Now, from my cape, I turn it into cloth, vellum cloth. This was a vellum configure cloth node, just like we saw before. There's nothing I've done to it whatsoever except lay down the vellum configure cloth. I laid down a vellum attach, and I said, hey, I want to attach a certain set of points, and that is these 6 points right here, 1, 2, 3, 4, 5, 6. And I want to attach them to the group called cape attach group. And if we want to see that cape attach group on the character so we can see exactly what it is, I can just do a quick blast over here. So here's the character, and we will blast away the cape attach group. And you can see that that's these polygons right here is where I want the cape to attach to. Okay, right here in front of the clavicle, kind of off of the neck a little bit. If I do delete non-selected, you can really see. So these are the points where I'm saying, hey, cloth, attach just to these primitives, okay? Not to the rest of the body, not to the rest of the neck, just to this specific area, okay? So right here and right here. Awesome. So that's what I do, vellum attach. Hey, these 6 points attach to somewhere on here, and you can already see that it went through and it found how to connect those. You might be thinking, but what if it goes through the character? How's that going to work? Well, let's watch. So here's the final character with the cape in T-pose, and I'm going to go 1 frame at a time. So the first frame, my cape automatically grabs or levitates towards that particular point where it attaches. But remember, even though we're using this vellum attach, what we're attaching to is the collision geometry. So it knows that the cloth is going to collide with anything that it comes in contact with. So as we move forward, we can see that it is seeking out those points on the geometry, okay? So we'll move back, and you can see the cloth seeking out those points on the geometry. It crawls along the surface of the geometry because it's a collision geometry until it finds the correct points to attach to, and it locks down onto those points, okay? So all I did was shape out a piece of cloth that I wanted by drawing it, and then just did a quick little mirror of one side, fused it together as a curve, made a planar patch, turned it into cloth, attached it to a part of my character that I wanted. I did do a little bit of vellum post-process to the cloth itself. I extruded it by its thickness, which we can look in here and actually see the effect of that. Right? So it does have a little bit of depth to it instead of being a singular plane. And I didn't even run a subdivision on it, and I'll show you what the result looks like. This is without even having the subdivision on it. So let's frame out here, and we'll just click play. So it's going to take just a second for this thing to get rolling, but here we go. So here's our animation. Here's our cloth cape on our character. And it's interacting nicely. It's following the shoulder connections where I wanted it to. It's reacting to the collisions of the character itself. And all of it was set up with about 4 vellum nodes without a single DOPS network, without any sort of complicated I/O. And I've got a cloth working on a character. Now I can make this look a lot better, of course, by adding pleats. I can add different kinds of attachment geometry to it. I could smooth it out with some more of the post-process. There's a lot of stuff that we can do with this to make it look even better, but I just wanted to show you for this course that the techniques and principles that we've used just by making a simple flagpole apply right here very easily to rapidly create functional cloth for a character. So you can kind of begin to art design this now. Maybe that's not the shape of the cloth that you wanted. Well, you can actually make the custom cape however you want it now, and then resimulate and up-res and make it look however you'd like. So I hope you've enjoyed this little brief intro and overview to how the new Vellum solver works, how the new unified solver's data flow works, the differences in working with Vellum in DOPS versus working with Vellum directly in SOPS. And I encourage you to explore anything that you want to in Vellum, and please bring it up in the office hour sessions that we have. Bring it up in the new instructor Slack channel. That would be awesome as well. Or just email me, johnm@sideeffects.com. And I am happy to help you out any way that I can. So I hope you've enjoyed this course, and I look forward to talking to you soon.